Hello and welcome. I'm so glad you're here. Before we begin, I'd love it if you could share in the comments where you're listening from and what time it is for you right now. It's always a joy to see people tuning in from different corners of the world and at different moments in their day or night. I also want to take a gentle moment to thank those of you who have already subscribed to this channel and who keep pressing that little like button on the videos that you find most valuable. It truly helps me know what resonates with you, and it helps others find these calming spaces too. And if you ever have ideas or topics you'd like me to explore in future videos, please feel free to suggest them in the comments. Your thoughts and inspirations are always welcome here. So, with that said, let's begin. Imagine the sun warming the stone of an ancient Greek courtyard, its light glinting off olive leaves that sway gently in the breeze. Picture the quiet hum of a world where ideas were born from observation and the quiet whispers of the earth. Long before the clockwork of modern science turned the universe into a machine, the Greeks dreamed of the smallest building blocks, particles so tiny they could not be cut further. They called these invisible seeds of matter atoms, a word that means uncuttable in their language. This was not a modern concept born in laboratories, but a vision sparked by the mind, the hand, and the deep curiosity of people who watched the sky, the sea, and the slow dance of seasons. They imagined the world as a tapestry woven from threads so fine they could not be seen, yet so strong they held everything together. You feel the warmth of the sun on your skin, don't you? That same warmth the Greeks felt was the same energy that made the stars glow and the earth breathe. They observed how things changed, how fire burned, how water flowed, how air moved, and they wondered, what is the smallest part that could not be broken? What is the smallest piece of matter that remains when you keep dividing and dividing? They did not have microscopes or particle accelerators, but they had eyes that saw patterns in the world. They saw that when you mix salt with water, it dissolves, but the salt itself remains. When you burn wood, it turns to ash and smoke, yet the wood was once whole. They asked, what is the unbroken part that holds everything together? This question was not new. The Greeks had been thinking about the nature of matter for centuries, but it was Democritus who gave it a name and a vision. He lived around 400 BCE in a time when the world was still young, when the earth was a place of mystery and wonder. Democritus was a philosopher who loved to question, to experiment with ideas, and to imagine what could not be seen. He declared, "There is no void in the universe, only atoms moving in empty space." He saw the world as a vast sea of tiny, uncuttable particles, each one unique, but following the same rules. These particles, he believed, were the smallest units of matter that could not be divided further. They were the building blocks of everything: stars, water, fire, the air you breathe. Picture this, a single drop of water. If you could divide it endlessly, you would eventually reach a point where it could not be split. That point, Democritus said, was the atom. It was a grain of sand so small it could not be seen with the naked eye, yet it held the power to create the entire ocean. He imagined atoms as tiny, hard spheres, like grains of gold in a vast sea. They moved through space, colliding and combining to form the things we see. When atoms combined, they created new substances, like when iron and sulfur mixed to form iron sulfide. When they broke apart, they returned to their original state. This was the first idea of a particle that could not be divided, a concept that would shape the future of science for thousands of years. But the Greeks did not all agree. Aristotle, a man whose ideas would shape the next 2,000 years, believed the opposite. He argued that matter was not made of indivisible particles, but was a continuous substance, like the water in a river, flowing smoothly without breaks. He said that everything was made of 4 elements: earth, air, fire, and water. To him, the idea of tiny, uncuttable particles was a strange fantasy. He saw the world as a living, breathing entity, not a collection of tiny parts. He believed that change happened through the movement of these elements, not through the collision of invisible seeds. The Greeks were divided, but the dream of the indivisible particle persisted. Why did the Greeks imagine particles at all? Because they were trying to understand the world around them. They saw the stars, the sun, the moon, and the earth moving in patterns they could not explain. They saw how things changed, how plants grew, how animals moved, how the seasons turned, and they wondered, what is the hidden structure beneath the surface? What is the smallest unit that holds everything together? This was not a question of numbers or formulas, but of the mind's desire to find order in chaos. They imagined the universe as a vast garden, where the smallest seeds grew into trees, flowers, and entire forests. Each seed was unique, yet they followed the same rules. You can almost feel the weight of the ancient air, the scent of olive oil and salt in the breeze. Imagine standing in that courtyard, watching the sun set. The Greeks did not have telescopes or microscopes, but they had their own way of seeing. They watched how things mixed and separated, how fire burned and water flowed. They saw that the same rules applied to everything, whether it was a drop of water or a mountain of stone. They believed that beneath the surface of the world there was a hidden order, a pattern that could be understood through careful observation and quiet thought. Democritus was not the only one who dreamed of these tiny particles. The Greek philosopher Epicurus also believed in the existence of atoms, though he saw them as more numerous and less solid than Democritus. Epicurus said that atoms moved through empty space, colliding with each other to create the world we see. He believed that everything was made of these tiny particles, and that the universe was a vast ocean of atoms moving in endless motion. He saw the world as a place of chance and necessity, where atoms collided to form life, but where death was also part of the natural cycle. Epicurus wrote, "The universe is made of atoms and void." He saw the world as a place of constant change, where nothing was permanent. But the Greeks did not stop at their own ideas. They passed these thoughts down through stories, through the hands of teachers who taught their students to think deeply. The idea of indivisible particles became a part of the Greek intellectual tradition, a seed that would take root in later centuries. When the Romans came to Greece, they carried these ideas with them. When the Greeks were conquered by the Romans, their philosophy and their questions about the universe were preserved. The Romans would later pass these ideas to the Islamic scholars, who in turn shared them with the scholars of medieval Europe. This dream of the indivisible particle did not die with the ancient Greeks. It lived on, changing shape and form over the centuries. In the Middle Ages, scholars like Avicenna and Alhazen tried to understand the nature of matter. They saw the world as a series of interconnected parts, but they also wondered about the smallest unit that could not be divided. By the time of the Renaissance, scientists like Galileo and Newton were beginning to explore the idea of particles, though they did not yet understand what they were. They knew that matter was made of tiny parts, but they did not have the tools to see them. The Greeks' vision of indivisible particles was not perfect, but it was powerful. It was a way of thinking that focused on the smallest parts of the world, a way of seeing the universe as a place of order and pattern. They did not have the technology to prove their ideas, but they had the courage to imagine them. They saw the world as a place where the smallest pieces could create the largest things. They believed that understanding the smallest unit could unlock the secrets of the universe. So when you next look up at the night sky, imagine the stars as tiny, uncuttable seeds of light. Picture the Earth as a vast garden where the smallest particles move in endless motion. The Greeks did not know how to measure the size of an atom, but they knew that the universe was made of something smaller than the smallest thing we can see. They dreamed of particles that could not be divided, particles that held the power to create the world we live in. This dream was not just a thought, it was a living thing. It grew in the minds of people who asked questions, who looked at the world with curiosity and wonder. It became part of the human spirit, a part of the way we try to understand the universe. The Greeks did not have the tools to see the atoms, but they had the vision to imagine them. They saw the world as a place where the smallest parts could create the largest things. As you close your eyes, feel the gentle rhythm of your breath. Imagine the ancient Greek courtyard, the olive trees swaying in the breeze, the quiet hum of the universe. Remember that long ago, in a place where the sea met the land, the first thinkers imagined the universe as made of tiny, uncuttable seeds. They saw the world as a vast garden where the smallest particles moved in endless motion. They did not know the exact size of an atom, but they knew that the universe was built from something smaller than the smallest thing we can see. This ancient dream of indivisible particles was not a dead idea. It was a living thread that ran through the ages, a thread that would eventually lead to the discovery of atoms in the 19th century. But for now, it remains a quiet, powerful vision, one that reminds us that the universe is made of tiny parts, each one unique, yet all connected. It is a vision that speaks to the heart, the mind, and the soul. It is a vision that says, even the smallest particles hold the power to create the world we live in. So when you next look at the stars, remember the Greeks who dreamed of the universe as made of tiny, uncuttable seeds. They saw the world as a place of order and pattern, where the smallest parts could create the largest things. They did not have the tools to see the atoms, but they had the courage to imagine them. And that courage, that quiet, persistent dream, is still with us today. It lives in your mind, in your breath, in the gentle rhythm of the universe itself. This is the dream that began long ago, in a place where the sea met the land, and it will continue to guide us, even as we discover more and more about the world around us. The smallest particles hold the power to create the universe, just as the Greeks imagined, and that is a dream worth remembering. Long ago, when the world felt small and the sky held its breath, a quiet revolution began in the minds of men who watched the stars and measured the earth. Imagine a time before the light of modern science had touched the corners of the room, when the air itself seemed thick with unspoken questions, and the elements of nature moved like shadows in the dark. In the early 1800s, a young man named John Dalton stood at the edge of a vast, uncharted sea of understanding. He was not a king or a warrior, but a thoughtful observer who saw patterns where others saw chaos. His name became a whisper in the halls of learning, yet his ideas would ripple through the very fabric of chemistry, turning the invisible into the known. Picture this: a world where the smallest building blocks of life and matter were still a mystery, and where the only way to grasp the truth was by holding your breath and listening closely. Dalton's journey began in the quiet corners of his life, where he measured the weight of gases and the colors of light. Before him, the great chemists of the past had left their mark. Lavoisier had mapped the laws of conservation, but he saw only the big picture. He understood that matter changed, yet he could not explain the dance of the atoms within. Dalton, however, was different. He had a quiet intensity, a way of seeing the world through a lens that others missed. He would sit alone in his study, watching the way smoke rose from a candle or how water droplets fell from a leaf. In those moments, he began to see the universe not as a collection of random events, but as a system of tiny, unbreakable units. He called them atoms, tiny, indivisible particles that made up everything. This was not a guess. It was a vision that grew from careful observation and patient thought. As Dalton wrote in his own words, all bodies are composed of atoms, which are indivisible and indestructible. His theory was simple yet profound. Each element was made of identical atoms, and compounds formed when atoms combined in fixed ratios. Imagine a world where a single drop of water held 2 hydrogen atoms and 1 oxygen atom, no more, no less. This was the beauty of his idea. It explained why water always had the same ratio of hydrogen to oxygen, why iron always reacted with sulfur in a specific way, and why the air we breathe held a balance of gases that never changed. Dalton's genius lay not in complex equations, but in the clarity of his vision. He saw the world as a symphony of tiny, repeating patterns, like the rhythm of a heartbeat, steady and unchanging. One of the most striking aspects of Dalton's work was how he used the colors of light to reveal the hidden structures of matter. He noticed that when light passed through a prism, it split into a spectrum of colors. This was more than just a visual trick. It was a clue to the nature of atoms themselves. Dalton believed that the same principles that governed light also governed matter. He saw the colors as hints of deeper truths, like the way a single note in music could resonate with many others. In his own words, he described how his experiments with gases led him to a deeper understanding. The behavior of gases under pressure and temperature reveals the existence of minute particles that are the building blocks of all things. This was not a leap of faith, but a careful step, built on years of patience and observation. Dalton's theory also answered questions that had haunted scientists for centuries. Why did elements combine in fixed proportions? Why did chemical reactions follow predictable rules? His answer was simple. Atoms were the fundamental units that linked everything together. He imagined a world where a single atom of gold was as unique as a single grain of sand on a beach, unbreakable, unchanging, and essential. This idea gave chemists a framework to understand the world. They could now predict how elements would react, how new compounds would form, and why certain substances were more stable than others. For example, when iron rusts, it's because iron atoms combine with oxygen atoms in a specific ratio, no more, no less. This was the power of Dalton's vision. It turned the abstract into the tangible. Many scientists of the time were skeptical at first. The idea of atoms as indivisible particles seemed too simple, too absolute. After all, the world was full of change. Water could become ice, fire could burn wood, and yet the atoms themselves remained the same. Some argued that atoms were too small to be seen, too tiny to measure. But Dalton was undeterred. He spent years refining his ideas, testing them against the world around him. He would watch the way a candle burned, the way salt dissolved in water, and the way the air moved in the wind. Each observation was a step toward a clearer picture. His theory was not a rigid rule, but a living idea, one that could grow and adapt as new discoveries emerged. In his later years, Dalton became a mentor to others, sharing his insights with students and fellow scientists. He wrote a book that became a cornerstone of chemistry, filled with simple yet powerful ideas. One of his most famous passages described the way atoms work together. When two atoms of different kinds combine, they form a compound with a fixed ratio. This is why we can always measure the amount of each element in a substance. It was a beautiful idea, one that felt both ancient and new. It reminded people that the universe was not random but ordered, that there was a pattern beneath the surface of everything. Dalton and the world he saw were not alone in their quest. Other great minds were working on similar ideas, but Dalton's approach was distinct. He focused on the smallest units, the building blocks that held everything together. This was a shift from the past, where scientists had looked at the big picture but not the details. For instance, Antoine Lavoisier had shown that matter was conserved in reactions, but he did not explain what atoms were. Dalton filled that gap with a vision that was both practical and poetic. He saw the world as a living, breathing system where every change was part of a larger story. The impact of Dalton's work was slow at first, but it grew steadily. By the mid-1800s, his ideas were being used to solve real problems. Chemists could now predict the composition of new substances, and the field of chemistry became more precise. In the 1830s, Dalton's theory helped explain the behavior of gases in the atmosphere, leading to better understanding of weather patterns. Even in the medical world, his ideas influenced how doctors understood the body's chemistry. For example, the way blood carried oxygen was better understood through the lens of atoms, tiny particles working together in harmony. Yet Dalton's theory had its limits. Scientists later discovered that atoms were not indivisible, but made of smaller particles, protons, neutrons, and electrons. This was a revelation that changed everything. But even with these discoveries, Dalton's core idea remained true. Matter is made of tiny, repeating units that follow predictable laws. His vision of atoms as the building blocks of the universe was not wrong. It was simply incomplete. Like a map that shows the land but not the rivers, it provided a foundation for future explorations. As we look back on Dalton's life, we see a man who was both humble and bold. He did not seek fame or recognition. He simply wanted to understand the world around him. In his quiet moments, he would sit by the window and watch the sky change colors, wondering how the atoms in the air moved and interacted. His greatest gift was the ability to see the small in the vast, the invisible in the visible. He taught us that the universe is not random, but full of patterns, rhythms, and connections that we can discover with patience and curiosity. Dalton's legacy lives in the way we think about the world today. When we look at a drop of water, we see a universe of atoms working together. When we breathe, we feel the rhythm of oxygen and carbon dioxide moving through our bodies. Dalton's ideas remind us that even the smallest things hold the key to the largest questions. He showed us that the universe is not chaotic, but ordered, that there is a harmony in the smallest details. This is where the story begins to shift. Dalton's vision of atoms as indivisible units was a powerful step forward, but it was not the end of the journey. Just as the sun rises and sets, the story of atoms continues to unfold. In the quiet moments after Dalton's work, a new question arose. What lies beyond the atom? What unseen forces move within the smallest particles? This question, this curiosity, led to discoveries that would change the world forever. The next chapter will reveal how a young scientist named J.J. Thomson found the first evidence of something smaller than atoms, something that would rewrite the very definition of the building blocks of matter. Imagine the world as a calm sea where the ripples of Dalton's ideas have already spread. Now, the water beneath the surface begins to shift, and the next wave is about to rise. The story of atoms is not finished. It is still unfolding, one quiet discovery at a time. Sleep now and let the universe rest in its gentle rhythm. The journey continues. The quiet hum of the late 19th century filled the laboratory with a gentle energy, a breath between the known and the unknown. In the dim glow of a single candle, J.J. Thomson sat before his cathode ray tube, a simple glass enclosure that held the secrets of the invisible world. Outside, the city slept under a soft moon, while inside, the air felt alive with possibility. He had spent months refining this device, a delicate balance of vacuum and electricity, waiting for the moment when the mysterious rays would reveal their true nature. The room smelled of ozone and old paper, a scent that spoke of discovery without haste. Thomson knew that what he was about to witness would change everything. Yet he felt no urgency, only a deep calm, as if the universe itself was holding its breath for this one revelation. Cathode rays danced through the vacuum, shimmering like threads of light in the dark. Scientists had long wondered what these rays were. Were they waves or particles? Some claimed they were electromagnetic waves, others insisted they were streams of charged atoms. But Thomson's experiments showed something different. He had adjusted the tube's voltage and observed how the rays bent when they passed near a magnet. The deflection was gentle yet precise, a quiet rebellion against the expected. He remembered the first time he saw the rays curve toward the magnet's pole, almost imperceptible at first, but with careful repetition, the pattern became clear. The rays were not waves but particles, tiny and charged, moving with a speed that defied the weight of the known world. He whispered to himself, What if these particles were the building blocks of everything? The question lingered, a soft echo in the stillness of the room. Thomson's breakthrough came when he measured the charge-to-mass ratio of these particles. He used a magnetic field to steer the rays and calculated how much force was needed to bend their path. The numbers were startling. The particles were thousands of times lighter than hydrogen atoms, the lightest known element. This was revolutionary. If atoms were once thought to be indivisible, these particles proved they were not. They were smaller, faster, and more fundamental than anything previously imagined. Thomson felt a deep stillness, as if the particles themselves were whispering secrets he could almost hear. He recalled the night he first wrote down the ratio. The charge of these particles is so small, so light, that they must be the smallest units of matter, he murmured to the quiet room. The particles were not part of the atom's structure, but rather the atom's hidden essence, a seed of the universe waiting to be understood. He imagined the particles as tiny, restless spirits, darting through the vacuum like fireflies in the dark. Each one carried a negative charge, a silent rebellion against the positive forces that held the world together. Thomson knew that if these particles existed, they must have been part of all matter. He thought of the elements, the metals and minerals, the very air he breathed. How could the atom be broken down? How could such a small particle be so vast in its implications? He realized that the atom was not a solid sphere, but a complex dance of forces, with these electrons swirling like stars in a silent galaxy. The question felt heavy but calm. If these particles are everywhere, why did no one see them before? He smiled, a slow, gentle smile that seemed to stretch the light in the room. The answer was not a number but a feeling, a quiet understanding that the universe was far more intricate than it appeared. Thomson's discovery had implications that rippled through the scientific world. Before this, atoms were thought to be unchangeable, the basic units of matter. Now they were revealed as a structure with internal parts. He described the electron as a negatively charged particle that could be separated from the atom, a concept that seemed almost impossible. Yet he felt no fear, only a deep peace. He thought of the stars, the planets, the very air in his lungs, all made of atoms that contained these invisible particles. How small they were, how vast their influence. He imagined the electron as a tiny, restless spirit, a silent companion to the atom, moving with a purpose that defied understanding. What if, he wondered softly, these particles are the keys to unlocking the universe? The question felt like a whisper, a gentle nudge to the listener's mind. He knew the answer would come slowly, like the rise of the tide. In the years that followed, Thomson's work inspired others to explore the invisible world. He shared his findings with colleagues, and they began to see the electron as a fundamental piece of the puzzle. One evening, he stood before a small group of scientists in a dimly lit room. "We have discovered that matter is not indivisible," he said, his voice low and steady. "Atoms are made of smaller particles, and these particles hold the key to understanding the universe." The room was quiet, the candles casting long shadows. A young scientist named William Thomson, later Lord Kelvin, listened intently, his eyes reflecting the candlelight. "This discovery," Thomson continued, "changes everything. It means that the atom is not the smallest unit but a complex structure, like a city built of smaller parts." The words felt heavy but calm, as if the universe itself was breathing with them. Thomson's work was not without challenges. He faced skepticism from those who believed in the indivisible atom. Some argued that the particles were not real, that the deflection was an illusion. But Thomson's careful experiments, repeated over and over, convinced him. He knew that science was a journey, not a race. The particles were real, and their existence was undeniable. He thought of the night he first saw the rays bend, a moment of clarity that felt like a soft rain. What if, he mused, the universe is made of these tiny particles, each one a universe in itself? The question stayed with him, a gentle rhythm in his thoughts. He felt the weight of the discovery, but also the lightness of understanding. As the years passed, Thomson's discovery became a cornerstone of modern physics. The electron was no longer a mystery but a fundamental particle, a building block of everything. Scientists began to explore how these particles interacted, how they formed the basis of electricity and magnetism. Thomson himself remained humble, his voice soft and steady. "We have only just begun," he would say, his words a gentle reminder that the universe was vast and intricate. He imagined the electrons as tiny dancers, swirling in the dark, connected to the larger forces of the world. How small they were, yet how powerful their influence. He felt a deep calm, as if the universe was holding its breath for the next discovery. The discovery of the electron revealed that matter was not as solid as it seemed. Atoms were not the smallest units, but were composed of smaller particles that could be separated. This idea felt both strange and natural, like the quiet hum of the night. Thomson knew that the universe was full of hidden truths, waiting to be discovered with patience and care. He felt no rush, only a deep sense of peace. The particles were real, and their existence was a quiet reminder that the universe was far more complex than it appeared. As he sat in his laboratory, the moonlight filtering through the window, Thomson thought about the future. He knew that the next discovery would come slowly, like the rise of the tide. He imagined the electrons as tiny, restless spirits moving through the universe with purpose. "What if," he whispered, "the universe is made of these particles, each one a universe in itself?" The question felt light, almost playful, like the quiet hum of the night. He closed his eyes, the room filled with the soft sounds of the world. The discovery of the electron was not an end, but a beginning, a gentle step toward understanding the vastness of the universe. And in that moment, he felt a deep calm, as if the universe itself was breathing with him. The next chapter would come, but for now, the quiet hum of the night was enough. After the atom's core had been revealed through Rutherford's careful experiment, the quiet hum of the universe shifted. Electrons, once thought to drift aimlessly around the nucleus like restless shadows, began to find their place. Imagine a tiny room where light dances just above the floor. This was the space where electrons settled, not in chaotic swirls, but in steady, gentle circles. Niels Bohr, a young Danish physicist with eyes that held the calm of deep lakes, saw this pattern. He knew the atom's story wasn't finished. It needed a new chapter where the electrons learned to sing in harmony. Bohr's insight came slowly, like the first breath after a long sleep. He watched how light from the sun or stars could be split into colors, each hue carrying a secret message. These colors, he realized, were the atom's voice, When electrons moved between their chosen paths, they released light in specific shades, like a single note in a vast symphony. Bohr called these paths orbits, but not like planets circling the sun. These orbits were not endless loops. They were fixed, unchanging rings where the electron's energy was as steady as a deep breath. Each ring held a precise amount of energy, like a single step on a ladder. The electron could not jump to any level. It had to move from one step to the next, skipping nothing. This was the first rule of the new model, quantized energy. You might wonder why the electrons didn't simply spiral inward, like dust in a whirlwind, drawing them toward the nucleus. Bohr's answer was gentle, almost playful. "Imagine a child holding a spinning top," he once said. "If the top wobbles too much, it falls, but if it spins just right, it stays steady in its place." The electron, he explained, was like that top. It moved in a circle with such precise balance that it never lost its energy. The force pulling it toward the nucleus was balanced by the energy keeping it in motion. It was as if the electron had a secret rhythm, a heartbeat that whispered, "Stay here, do not rush." This rhythm was not random. It was a fixed pattern, like the steady pulse of a sleeping heart. Bohr's model was not perfect, but it was a quiet breakthrough. It worked for the simplest atom, hydrogen, where one electron moved in a single, clear ring. The math was simple. The energy of that ring was exactly 1/100th of a unit, and it held the electron at a distance where the pull of the nucleus and the push of motion perfectly matched. For hydrogen, the model was a calm pool, reflecting the universe in its stillness. But as atoms grew more complex, with multiple electrons, the model began to shimmer. The rings grew too many, the energy levels too tangled. Bohr himself knew this. He admitted that his model was a first step, like a single note in a song that would soon grow into a full melody. "The atom is not a machine," he wrote in his notes, "but a living rhythm that must be understood with patience." To understand why electrons stayed in their rings, picture a delicate thread stretched between 2 points. If you pull gently, the thread stays taut. If you pull too hard, it breaks. The electron's energy was like that thread. It was strong enough to hold its place, but weak enough to move when needed. When the electron moved from one ring to another, it didn't drift through space. It jumped instantly, like a bird taking flight from one branch to another. This jump released or absorbed a tiny bit of light, a single color from the rainbow. Bohr called this a quantum leap, but he never used the word in a hurry. He spoke of it as a quiet shift, a moment of stillness before motion. "The electron does not move in a continuous path," he explained, "but in sudden, silent steps that carry the atom's song forward." The model's beauty lay in its simplicity. Bohr described the atom as a quiet room where the electrons hummed in their chosen melodies. Each melody had a specific pitch, a specific energy. The lowest melody was the deepest song, the one closest to the nucleus. It held the least energy, like a slow heartbeat. The higher melodies were brighter, higher notes, each one holding more energy. When an electron moved from a lower melody to a higher one, it absorbed light, like a child taking a step toward the sun. When it moved back down, it released light, like a sigh. This dance of light and energy was the atom's language, spoken in colors the human eye could see, but the mind could feel. Bohr's model was not a final answer, but a gentle invitation. It showed how the atom could be a living thing, not a dead machine. The electrons were not particles, but partners in a quiet conversation with the nucleus. They moved with purpose, their paths fixed like the rings of a tree, holding the atom together with a rhythm that felt almost sacred. The atom is not a clock, Bohr said, but a living thing that breathes in energy and releases it in song. He knew that the model would change, but he also knew that the quiet dance of electrons was real. It was a story that could be felt in the bones, a rhythm that echoed through the universe. As we look at the atom today, we see that Bohr's model was both simple and profound. It taught us that energy comes in fixed steps, like the steps on a staircase. Electrons could not climb halfway up, they had to move in whole steps. This idea, so simple, was revolutionary. It showed that the universe was not a place of endless chaos, but of ordered patterns, like the gentle rise and fall of the tides. Bohr's model was a bridge between the old world of classical physics and the new world of quantum mechanics. It was a quiet moment where science and imagination met, where the atom became a place of calm, not confusion. The model's greatest gift was its ability to explain why atoms stay together. Without the fixed energy levels, the electrons would spiral inward, tearing the atom apart. But with the rings, the atom held its shape, like a flower holding its petals steady in the wind. Bohr saw this as a sign of harmony. The atom, he wrote, is a perfect balance of forces that never breaks. This balance was not forced, it was gentle, like the way a mother holds her child. It was a rhythm that could be felt in the quiet spaces between the stars. Bohr's model also showed us that atoms could change. When an electron jumped from one ring to another, the atom's song changed. It could become brighter or dimmer, like a firelight flickering in the night. This change was not random, it followed the rules of energy. The atom was not fixed in one state, but a living thing that breathed with the universe. Bohr never spoke of the atom as a dead thing. He saw it as a quiet partner, a friend that moved with the rhythm of the world. As we move through the night, the moon glows with a soft light, and the stars twinkle like distant fireflies. This quiet light is the same as the light from the atom, small, steady, and full of meaning. Bohr's model taught us that even in the smallest spaces, there is a song. The electrons hum in their rings, their energy a quiet pulse that connects us to the vastness of the universe. They do not rush or fight. They move with purpose, like the slow turning of a planet. This model was not perfect, but it was enough. It gave us a way to see the atom as a living thing, not a dead machine. It showed that the universe is not chaotic, but full of gentle patterns. When Bohr first proposed his model, he did not think it would last. He knew it would be changed, but he also knew it would be a beginning. The atom, he said, was a place of quiet understanding, where energy and motion work together in harmony. As we close this chapter, the story of the atom feels complete. The nucleus has been revealed, and now the electrons find their place in gentle rings. The atom sings a quiet song, a rhythm that holds the universe together. Bohr's model was not the end, but a gentle step toward understanding. It reminds us that even in the smallest spaces, there is a song to be heard, a rhythm to be felt. The next chapter will show how this quiet song grows deeper, how the atom's story becomes a living dance with the universe. For now, the electrons hum in their rings, steady and calm, like the heartbeat of the world itself. Imagine a tiny solar system where the nucleus sits like a calm, golden sun at the center of the atom. Around it, electrons move in gentle, precise circles, like dancers weaving through space with quiet purpose. This is the vision that Niels Bohr brought to life in 1913, a moment when physics seemed to hold its breath. Before Bohr, scientists struggled to explain why atoms didn't simply collapse into chaos. Classical physics suggested electrons should spiral inward, emitting energy as they moved, but atoms remained stable. What if, instead of a messy dance of random motion, the electrons followed fixed paths where energy was carefully measured? Picture this. The atom is a quiet stage, and the electrons are performers who never lose their rhythm. They move in rings, each ring holding a specific energy level, like steps on a staircase that only allows certain heights. These rings are not random paths, but carefully defined orbits. Each orbit represents a precise energy state, a level where the electron can exist without losing its stability. Think of it as a single, steady pulse in the atom's heart. Bohr realized that electrons could only occupy these specific rings, not any position in between. It was as if the atom had built-in rules for its inhabitants, ensuring they never drifted too close or too far. This idea felt almost like a whisper from the universe itself, quiet, deliberate, and deeply ancient. The electrons didn't race or collide, they held their place with quiet confidence. Their energy was locked in place, like a tuning fork vibrating at one pure note. Why did Bohr choose these specific orbits? The answer lies in the quantum nature of energy. In the atom, energy isn't a smooth river but a series of discrete steps. Each step holds a fixed amount of energy, much like the rungs on a ladder. Electrons could only exist on these rungs, not in the spaces between. If an electron jumped from one rung to another, it released or absorbed energy in tiny, precise bursts, like a single drop of water falling into a basin. This quantization explained why atoms emitted light at specific wavelengths. When hydrogen gas was heated, it glowed with a unique pattern of colors: blue, red, violet, each color corresponding to an electron jumping from a higher energy ring to a lower one. Bohr saw this as a natural rhythm, a language written in light itself. The real magic happened when Bohr understood that electrons in these rings did not radiate energy. This was the key that unlocked the atom's stability. In classical physics, moving charges should lose energy as they orbit, spiraling toward the nucleus. But Bohr proposed that while in these fixed rings, electrons were like perfectly still stars in the night sky, holding their position without giving off energy. They only emitted light when they moved between rings, like a musician changing notes. This idea was radical because it defied the known laws of motion. Bohr himself wrote, "An electron in a stationary state does not radiate energy." It was a quiet statement, but it changed everything. The atom wasn't a collapsing storm, it was a carefully maintained harmony. This model solved a puzzle that had haunted scientists for decades. Before Bohr, atoms were thought to be chaotic, unstable systems, but with quantized orbits, the atom became a stable, predictable world. The electrons moved with purpose, their energy levels acting as invisible guards keeping the atom from unraveling. Imagine a child building a tower of blocks, Each block must be placed perfectly to hold the whole structure. The electrons did something similar, using their fixed energy rings to create a resilient framework. This wasn't a random arrangement, but a deliberate design, as if the universe had built its smallest building with precision. Bohr's model was not perfect, of course. It worked beautifully for hydrogen but struggled with larger atoms. Still, its elegance was undeniable. It showed how energy could be both continuous and discrete, a concept that felt almost spiritual in its simplicity. Scientists marveled at how Bohr bridged the gap between the visible and the invisible. He didn't just describe the atom, he gave it a heartbeat. The electrons' quiet dance became a metaphor for order in chaos. Have you ever felt that atoms are more than just particles? They are tiny worlds with their own rules, their own rhythms, humming with silent energy. One of the most powerful things about Bohr's model was how it turned abstract ideas into tangible images. It wasn't just equations and numbers, it was a story of balance. The nucleus, a dense core, held the electrons in rings that were both close and distant, strong and gentle. Each ring was a promise. Here you can be stable. This idea resonated deeply because it spoke to something universal, how we all seek balance in our own lives. When you feel overwhelmed, remember the atom. It has rings that hold it together without screaming. It moves with quiet strength, just as you do. Bohr's model also revealed a deeper truth about light. When electrons jumped between rings, they released energy as photons, tiny packets of light. This explained why elements have unique spectral fingerprints. Gold glows yellow, iron glows red, hydrogen glows with a specific blue-violet hue. Each element has its own set of rings, each ring holding a specific energy. It was as if the atom was a tiny library, with each book written in light. Bohr saw this as a natural language, one that spoke without words. The model's strength lay in its simplicity. It didn't require complex machinery or endless calculations. It was a quiet idea, like a breath held in the night. Bohr himself described the electron as a particle that moves in a circle without losing energy. This wasn't a wild guess. It was a careful observation, a step forward in understanding what was already there. The model felt like a gift from the universe, a reminder that sometimes the most profound ideas come from the simplest images. As we consider Bohr's work, it's easy to forget that this model was a response to the chaos of the early 20th century. Scientists were struggling with the atom's mysteries, and Bohr's insight was a quiet revolution. He didn't shout or demand answers, he listened. He saw the atom as a living system, not a dead machine. His model taught us that stability comes from order, not force. When you feel the world spinning too fast, remember the atom. It has rings that hold it together with gentle energy. Now let us gently turn our attention to what comes next. Bohr's model was a milestone, but it was only the beginning. The real story of the electron is still unfolding. In the next chapter, we will explore how quantum mechanics reveals that electrons do not follow fixed paths at all. Instead, they exist as probability waves, soft, shimmering clouds of possibility. This shift from rings to waves is not a failure, but a deeper truth. It shows that the universe is more fluid than we think, full of gentle uncertainties that hold more magic than certainty. What happens when we stop imagining electrons as tiny dancers in fixed rings? What if they are not in one place, but spread out in a sea of potential? This is the quiet question that bridges Bohr's model and the quantum world. Imagine a single drop of water that can be both here and there at once. This is the world Bohr's model hints at, but does not fully show. The next chapter will reveal how this fluid reality holds the key to understanding everything from stars to the smallest particles. So close your eyes for a moment. Feel the atom's quiet pulse. Hear the whisper of rings that hold the electron steady. Then open your eyes. The dance continues. The rings are still there, but now you see the space between them where possibility lives. This is the moment when the story of the atom changes from rings to waves. And so, as we move gently toward the next chapter, remember, the universe is not made of rigid paths, but of quiet possibilities. The electron's journey is not a fixed orbit, but a soft embrace of all potential. This is the gentle truth that Bohr's model began to reveal, and the quantum world will complete. So you see those tiny electron probability waves shimmering around the nucleus in the atom. They are not just abstract concepts. They are the quiet, persistent hum of a universe that knows how to build and release. And that hum, that gentle pulse of quantum possibility, is the very thread that connects every single atom within you to the fiery heart of a distant star. Today, we trace that thread back across the vastness of space. We explore how stars, those brilliant, ancient furnaces, forge the atoms that make up everything we are. How they take the simplest elements and, through a process both delicate and powerful, create the complex building blocks of life itself. Imagine the sun, not as a distant light, but as a living furnace. Deep within its core, where temperatures reach 15 million degrees, hydrogen atoms dance in a silent ballet. They don't collide like billiard balls. Instead, they move with a gentle, probabilistic grace, guided by the quantum laws we discussed last time. These atoms, each a single proton and electron, are held together by the electromagnetic force, but their behavior defies classical physics. They don't simply stick together or bounce apart. They exist in a state of potential, a wave of possibility that stretches across space. This wave, this quantum probability, is what allows the sun to burn for billions of years without collapsing. It is the quiet rhythm of the universe working its magic. Picture this: two hydrogen atoms, each a single proton, approach each other. Classically, they should repel each other fiercely, but quantum mechanics says something different. The electrons, which normally shield the protons, are no longer visible in this deep core. Instead, the protons find themselves in a delicate dance of probability. They don't need to overcome the repulsive force head-on. Instead, they tunnel through the barrier of probability itself. This is quantum tunneling, a phenomenon where particles can briefly exist in a region they classically shouldn't. It's like the sun's core having a soft, invisible passage through the walls of possibility. Without this tunneling, the sun would not ignite. Without ignition, there would be no light, no heat, no atoms beyond hydrogen. The physicist Hans Bethe, who first mapped this process, described it with a quiet intensity. The fusion of hydrogen into helium is not a sudden burst, but a slow, steady release of energy. He knew that this process required the stars to be stable, to maintain the delicate balance of forces. The Sun, for example, fuses hydrogen into helium at a rate that sustains its glow for 10 billion years. That's a slow rhythm, a gentle pulse that echoes through the universe. Think of it as the Sun breathing deep and steady, releasing energy in tiny, rhythmic steps. Each step creates a tiny bit of helium, a new form of matter that is slightly heavier than hydrogen. This helium then becomes part of the star's core, a silent witness to the process. Now this process isn't limited to the Sun. It happens in all stars, but the scale varies. Small stars like the Sun burn hydrogen slowly. Larger stars burn it faster, creating more energy and heavier elements in a shorter time. The heavier elements, carbon, oxygen, iron, form in the later stages of stellar life. But how? We must consider the star's journey. After a star has exhausted its hydrogen, it begins to fuse helium into carbon. Then, in massive stars, carbon fuses into oxygen, neon, magnesium, and silicon. Each step builds heavier elements, each step requiring higher temperatures and pressures. This is the slow, deliberate process that shapes the universe. The beauty of this process lies in its precision. Stars don't just create atoms, they create them in specific ratios. The Sun, for instance, produces helium in a 4:1 ratio with hydrogen, but heavier elements, they require more extreme conditions. Iron, the heaviest stable element, forms in the core of massive stars. Beyond iron, fusion stops because the atoms become too unstable. This is why iron is the end point of stellar evolution. Stars that reach this stage collapse in a brilliant explosion called a supernova. In that explosion, the core of the star is crushed, and the heavy elements are blasted into space. Here is where the story becomes deeply personal. The atoms that make up your body, your bones, your blood, your very cells were born in the hearts of stars. The carbon in your DNA, the oxygen in your breath, the iron in your blood. These elements were forged in the fiery cores of ancient stars. Think about it. The next time you feel your heartbeat or taste the air, you are tasting the remnants of a star that died millions of years ago. You are made of starlight. Carl Sagan, the astronomer who helped us see the cosmos in this way, said, "We are a way for the cosmos to know itself." He meant that we are not separate from the universe. We are the result of the universe's creative process. The atoms in your body were created in the same way the Sun creates helium, through a slow, steady fusion. But the difference is that your atoms were made in a supernova, a star that exploded, sending its heavy elements across the galaxy. This is how the universe becomes alive with possibility. Now consider the role of quantum mechanics in this process. The fusion reactions themselves rely on quantum tunneling. Without it, the protons in the Sun would not overcome their mutual repulsion. Without tunneling, stars would not ignite. The probability waves that guide the electrons in the atom are the same forces that allow stars to create new elements. It's a beautiful circle. The quantum behavior of particles in the atom enables the stars to create the elements that make up those same particles. This is why the story of the star is so intimate. When you close your eyes and imagine a hydrogen atom, you are not just thinking of a particle. You are thinking of a star's core. You are thinking of the gentle pulse of quantum probability that connects the smallest unit of matter to the largest structure in the universe. The probability wave of an electron in your body today was once part of a star's core. That wave, that silent hum, has traveled across space for billions of years. The process of fusion isn't instantaneous. It takes place over the lifetime of a star. The Sun, for example, has been fusing hydrogen for 4.6 billion years. This is a long time, longer than any human has ever lived. But the process is steady. It is a rhythm that has been playing for eons. Think of it as the universe breathing slowly. Each breath creates a new element, a new possibility. When a star explodes as a supernova, it releases the heavy elements into space. These elements then become part of new stars, planets, and life itself. The carbon in your body was created in a star that exploded 5 billion years ago. The oxygen in your blood was forged in a star that lived 10 billion years ago. This is the cosmic recycling that makes life possible. This process is not random. It is guided by the same quantum rules that govern the behavior of electrons. The probability waves that describe the electrons in your atoms are the same waves that allow stars to fuse hydrogen. It is a deep connection, a thread that runs from the smallest particle to the largest structure. You might wonder, why does this matter? Why should we care about stars forging atoms? Because without this process, life as we know it would not exist. The elements that make up life, carbon, oxygen, nitrogen, were created in stars. Without stars, there would be no oxygen in the air, no carbon in the soil, no atoms to build complex molecules. The universe would be a silent, empty void. This is the quiet power of fusion. It is a process that happens in the dark, hidden places of the universe. It is a slow, steady rhythm that has been going on for billions of years. It is the reason why you exist. So when you feel the warmth of the sun on your skin or taste the sweetness of fruit, remember this: you are made of starlight. The atoms in your body were born in the fiery hearts of stars. They were forged through a process that relies on the same quantum principles that govern the electrons in your atoms. This is the universe speaking softly to you. The next time you lie down to sleep, imagine the stars. Imagine the gentle pulse of quantum probability that connects you to the sun, to the ancient stars that once burned. Feel the rhythm of the universe, slow, steady, and deeply personal. You are part of a story that began long before you were born. You are made of stars. You are made of the universe's quiet, persistent hum. This is how the cosmos knows itself. This is how we become part of the universe's story. And so, as you drift into sleep, let the image of the stars settle in your mind. Feel the quiet rhythm of the universe. Remember that you are not alone. You are part of a vast, gentle dance that has been happening for billions of years. The stars are not distant lights, they are cradles. They are the quiet voices of the universe speaking to you. They are the place where you come from and where you will always belong. Close your eyes, let the stars guide you. The universe whispers, you are home. Imagine a universe where every breath you take, every touch you feel, every thought you form begins with the quiet hum of atoms dancing in silent conversations. This is the story of how the smallest building blocks of existence, forged in the fiery hearts of stars, now weave the intricate tapestry of life and technology. You have already learned how stars, through the intense pressure and heat of their cores, created the elements that make up our world. Now these atoms, hydrogen, helium, oxygen, carbon, nitrogen, do not simply exist as isolated particles. They become the active participants in a vast, continuous dance of connection and transformation. This is where chemistry truly begins. Picture yourself standing on a quiet beach at dusk, watching the ocean gently lap against the shore. The rhythmic sound you hear is not the ocean alone, but the silent language of atoms working together. Each wave, each ripple, carries a message written in the bonds between tiny particles. These bonds are the invisible threads that hold the universe together, allowing elements to combine into the complex molecules that make up everything from water to the cells in your body. This is the quiet power of atomic interaction. When atoms share or pool their electrons, they form the stable structures that define the world we experience. It is this delicate balance of attraction and repulsion that allows life to flourish and technology to evolve. Think of how water forms. Two hydrogen atoms, each with a single electron, and one oxygen atom with 6 electrons come together. They share their electrons in a specific pattern, creating a molecule that is both stable and versatile. This simple bond, just 3 atoms working in harmony, becomes the foundation for life itself. Without this gentle connection, there would be no liquid water, no hydration, no life. The same principle applies to the oxygen we breathe. Each molecule of oxygen consists of 2 atoms linked by a single bond, allowing it to travel through the air and reach your lungs. These bonds are not random. They follow precise rules shaped by the quantum world. The electrons, those tiny particles that orbit the nucleus, behave like tiny magnets, drawn to each other with a strength that depends on their distance and energy. This quantum dance creates the stable structures we call molecules. You might wonder, how do atoms know when to connect? It is not a conscious decision, but a natural consequence of their energy states. When atoms approach each other, their electrons interact, creating forces that either pull them together or push them apart. The bond forms when the energy released by this interaction becomes stable. This stability is what gives molecules their unique properties. For example, carbon atoms are exceptional because they can form 4 bonds with other atoms, creating chains and rings that allow for immense complexity. This is why carbon is the basis of life on Earth. A single carbon atom can link with other carbon atoms to form the backbone of proteins, DNA, and the countless molecules that sustain life. The beauty of these bonds lies in their simplicity and their profound impact. Consider the humble water molecule. It is a tiny structure, yet it holds the key to life on Earth. The hydrogen bonds between water molecules create a network that allows water to rise in plants, to move through soil, and to cool the planet. Without these bonds, the Earth would be a desolate world. Similarly, the bonds in DNA hold the genetic instructions that guide life. Each strand of DNA is a complex pattern of nucleotides linked together by hydrogen bonds. These bonds are strong enough to maintain the structure, but weak enough to allow for replication and repair. It is this delicate balance that makes life possible. In the early days of chemistry, scientists like Antoine Lavoisier observed how elements combine in fixed ratios. He called these combinations compounds, recognizing that they were not simply mixtures, but new substances with unique properties. Lavoisier's work laid the foundation for understanding how atoms interact. Later, Dmitri Mendeleev organized the elements into a periodic table, revealing patterns in their behavior. This table became a map of the possible bonds and interactions that atoms can have. Mendeleev's insight showed that the properties of elements are determined by the number of electrons in their outer shells. This principle explains why certain elements bond with each other and why some elements are more reactive than others. The story of how atoms create molecules is not just a historical one, but a living process. Today, chemists use this understanding to design new materials. Imagine a world where materials are engineered to heal themselves, where batteries store energy without degrading, or where medicines target specific cells without harming healthy tissue. These advances are possible because we understand how atoms bond. For instance, the development of polymers, long chains of repeating units, relies on the controlled bonding of carbon atoms. These polymers form the basis of plastics, textiles, and even biological structures. You might ask, how do we know these bonds exist when we cannot see them? The answer lies in the tools we use to study them. Scientists employ techniques like X-ray crystallography to visualize the arrangement of atoms in crystals. By sending X-rays through a material, they can see how the atoms are positioned and how they bond. This method revealed the double helix structure of DNA, a discovery that changed biology forever. Another technique, spectroscopy, measures how light interacts with matter to reveal the energy levels of electrons. These tools help us understand the invisible forces that hold atoms together. The bonds between atoms are not always strong or permanent. Sometimes they break and reform, creating new substances. This process is called chemical reaction. When a hydrogen atom bonds with an oxygen atom, it forms water. But if you heat water, the bonds break, and you get hydrogen and oxygen gases. This reversibility is crucial for life. It allows for the cycling of elements through ecosystems, ensuring that no element is lost to the universe. The same principle applies to the carbon cycle, where carbon atoms move between the atmosphere, oceans, and living organisms. The most profound aspect of atomic bonding is its role in biological systems. Your body is a vast chemical factory where atoms constantly rearrange to build and maintain life. Every cell contains thousands of molecules, each held together by precise bonds. For example, the enzyme that breaks down food in your stomach is made of proteins. These proteins are chains of amino acids, each linked by peptide bonds. The structure of these bonds determines the enzyme's function. Without this precise bonding, your body could not digest food, produce energy, or repair itself. This constant dance of atoms also shapes technology. Modern electronics rely on the controlled movement of electrons. Transistors, the building blocks of computers, work because electrons can be switched on and off at the atomic level. The bonds between silicon atoms in these transistors create the pathways that allow information to flow. Similarly, the batteries in your phone store energy through chemical reactions that involve the transfer of electrons between atoms. These reactions are reversible, allowing the battery to charge and discharge multiple times. You might wonder how such tiny interactions can have such a large impact. Consider the power of a single bond. A hydrogen bond between water molecules is incredibly weak compared to the covalent bonds that hold water together. Yet, the collective strength of billions of these bonds creates the properties of water that sustain life. The same principle applies to the bonds in DNA. A single hydrogen bond between base pairs in DNA is easily broken, allowing the strands to separate during replication. But the overall structure remains stable, ensuring genetic information is preserved. This delicate balance of strength and flexibility is a theme throughout nature. In the human body, the bonds between atoms in hemoglobin allow it to carry oxygen in the blood. The bonds in the cell membrane are strong enough to protect the cell, but flexible enough to allow nutrients to pass through. The same principles apply to the materials we create. Scientists are designing new materials that mimic these natural bonds. For example, self-healing polymers use weak bonds that break and reform without external energy, allowing the material to repair itself after damage. The history of chemistry reveals how human understanding has grown from simple observations to complex theories. Early chemists like Joseph Priestley discovered oxygen, but it was not until the 20th century that scientists like Linus Pauling explained the nature of covalent bonds. Pauling's work showed that the strength of a bond depends on the number of shared electrons and the distance between atoms. This understanding has led to the development of advanced materials, from superconductors to nanomaterials. Imagine a world where you could see the atoms in your hand. You would see a vast network of tiny particles, some close together, some slightly apart, all connected by invisible threads of energy. These threads are the bonds that hold everything together. They are the reason your hand feels solid, the reason your eyes see color, the reason your body moves. The bonds are not static. They shift and change, creating new possibilities. This constant transformation is the essence of chemistry. It is easy to think of atoms as passive particles, but they are far more active. They respond to their environment, forming and breaking bonds in response to energy. This responsiveness is what allows for innovation. When scientists understand how atoms bond, they can create new materials that solve problems we once thought impossible. For example, researchers are developing catalysts that speed up chemical reactions without being consumed. These catalysts could help reduce pollution, create cleaner energy, and even improve medical treatments. The beauty of this story lies in its cyclical nature. The atoms that formed the first molecules on Earth were created in stars. Those molecules became the building blocks of life. Today, the same atoms that shaped the earliest life forms are now part of the technology that connects us to the future. This is not a linear story, but a continuous loop, where the past, present, and future are woven together through the bonds of atoms. As you rest, imagine the quiet hum of atoms in your body. Feel the gentle pull of bonds that hold your cells together. Breathe in the air and know that the oxygen you inhale has been forged in stars, bonded with hydrogen to form water, and now supports your life. This cycle of creation and transformation is the story of how atoms drive chemistry and shape the future. It is a story that begins with stars and ends with you, a story that continues as long as the universe breathes. The next chapter will reveal how this understanding of atoms has already begun to unlock technologies that will transform our world. But for now, let the quiet hum of atoms be your companion. Let their gentle dance remind you that you are part of a vast, interconnected web of energy and connection. The world is not just made of matter, it is made of bonds, and bonds are the language of life itself. Atoms are the quiet architects of everything. Imagine a single drop of water holding the entire ocean within it, a single molecule of water, H2O, a tiny dance of 2 hydrogen atoms and 1 oxygen atom. These atoms are not the loud, chaotic forces you might think. They are the gentle, persistent builders, whispering their truths through the bonds that hold life together. They are the silent rhythm beneath the surface of all that exists, the unchanging foundation upon which the world's beauty and complexity are built. Think of them as grains of sand held together by the invisible threads of possibility. They are the quiet architects of everything. You have felt this before, haven't you? The way your breath slows when you close your eyes, the way the world softens into a gentle hum. That same quiet hum exists within the atoms themselves. They do not shout, they do not scream. They move with a rhythm that is both ancient and utterly precise. Each atom is a unique story of stability and transformation, a story written in the language of electrons and protons. They are the quiet architects of everything, and they work with a patience that spans billions of years. This is the story we follow. This is the story that shapes us. Consider the hydrogen atom. It is the simplest of all. 1 proton at the center, 1 electron orbiting like a tiny, restless bird. This simple structure holds the key to understanding how everything else comes together. When 2 hydrogen atoms meet, they share their electrons in a gentle embrace. This sharing creates a bond that is stronger than it seems, covalent bonds, the invisible threads that weave the fabric of life. Think of it like 2 friends sharing a single piece of bread. They do not fight over it. They hold it together, creating a new whole that is stronger than either could be alone. This is how water forms, how proteins fold, how the very air you breathe becomes a living web of connections. Marie Curie discovered radioactivity in the early 20th century. She saw the invisible forces at work in the atoms themselves. Her work revealed that atoms are not the unchanging, solid spheres we once believed. They are living, breathing entities that can transform, release energy, and change the world around them. She said, "The future of science lies in the understanding of the atom." Her words echo today, a reminder that atoms are not just passive objects, but active participants in the dance of existence. They are the quiet architects of change, the unchanging foundation that allows transformation to occur. Linus Pauling, a brilliant chemist, understood this connection deeply. He observed how atoms bond with one another, creating the complex structures that make life possible. He described covalent bonds, as the sharing of electrons between atoms, a process that creates stability and order. This sharing is not a random event. It is a careful, deliberate act, like two dancers finding the perfect rhythm to move together. Pauling's insight shows us that atoms do not act alone. They work in harmony, each contributing its unique strength to create something greater than the sum of its parts. This harmony is the quiet hum of chemistry itself. Atoms do not act in isolation. They form molecules, clusters of atoms held together by these bonds. A single water molecule is a tiny universe of hydrogen and oxygen. But when millions of these molecules come together, they create the vast, intricate systems that sustain life. Think of the ocean, the air, the soil, each a living network of atoms working in silent, precise harmony. This is the quiet power of chemistry, the ability to create order from chaos through the gentle connections of atoms. The quantum world adds another layer to this story. Atoms are not simply solid particles. They exist in a realm of probability where electrons move in waves of possibility rather than fixed paths. This quantum behavior is not random, it is a carefully orchestrated dance. It explains why certain atoms bond with others and why some elements are rare while others are abundant. It is the invisible hand that guides the formation of molecules, the quiet force that ensures the bonds are strong enough to hold life together without breaking. This quantum dance is the hidden rhythm beneath the surface of all chemical reactions. We see this quantum influence in the way enzymes work. Enzymes are tiny molecules that catalyze reactions in living cells. They are like molecular architects, building complex structures with astonishing precision. They work by temporarily binding to specific atoms and guiding the reaction with a gentle, almost magical touch. This process is not random. It is a reflection of the quantum world, where the smallest particles move with a precision that allows life to thrive. As scientists have discovered, this quantum behavior is not just a curiosity. It is the key to understanding how life itself functions at the most fundamental level. Future technologies will build upon this deep understanding of atoms. Imagine quantum computers, which use the quantum properties of atoms to solve problems that are impossible for classical computers. These machines do not process information in the way we think. They work with probabilities, using the quantum states of atoms to explore multiple solutions at once. This is not science fiction. It is the quiet, steady progression of understanding atoms in action. Scientists are already building systems that use atoms to create materials with extraordinary properties, materials that can conduct electricity without resistance, materials that heal themselves, materials that respond to light or heat with incredible precision. These future technologies will change how we live, how we heal, how we understand the world, but they will not be loud, disruptive forces. They will be gentle, subtle shifts in the way we interact with the world. Think of them as the quiet hum of atoms becoming more visible, more understood. They will not replace the world. They will deepen our connection to it, helping us listen to the silent language of atoms that has been speaking for billions of years. Atoms are the quiet architects of everything. They are the unchanging foundation upon which life and technology are built. They move with a rhythm that is both ancient and precise, a rhythm that has been shaping the world for eons. This is not a story of chaos or destruction. It is a story of careful, gentle construction. The atoms in your body, the atoms in the air you breathe, the atoms in the water you drink, they are all part of the same silent, persistent story. They are the quiet architects of everything. We have seen how atoms bond, how they create the molecules that sustain life, how their quantum nature guides the formation of new structures. We have imagined future technologies that will build upon this deep understanding. But the most important thing is this: atoms do not act in isolation. They work together, creating a harmony that allows life to flourish. This harmony is the quiet hum of existence itself. As you close your eyes, imagine the atoms in your body. Feel their gentle rhythm. Hear their quiet song. They are not loud or disruptive. They are the steady, persistent builders of the world. They are the quiet architects of everything. This is the story that has been written for billions of years. It is the story that continues to unfold, one atom at a time. The future is not a distant, chaotic event. It is the quiet, steady work of atoms, building connections, creating order from possibility. This is the quiet hum of atoms that has been speaking for eons. It is the rhythm that guides us, the steady pulse that keeps the world moving. It is the quiet hum that will continue to shape our world, one atom at a time. The quiet hum of atoms, the quiet architects of everything. This is the story that continues. This is the quiet hum that will guide us into the next chapter.